Hi and welcome to the last little section of our Module 7 Inquiry Question 5, and we're looking today at soaps and detergents. So our outcome that we're going to investigate is the structure and the action of soaps and detergents. So most of you know that we're using soaps and detergents to clean ourselves, our clothes, our dishes, and our cars, anything really that's dirty and requiring cleansing. So the great thing about soaps and detergents is they're able to move dirt, our oils, and even our stains. And this is due to the structure of the soaps and the detergent molecules, and it's really enabled scientists to develop more cleaning products. So over the years, we've seen an increase in the number of cleaning products available to us. Old days gone by, a little bit of sunlight soap, give our clothes a bit of a clean, and that did the job. Now we're seeing action and spray cleansers and so forth, even little special containers that are designed to remove blood or biro or glue or whatever else you've got on your clothes, and that's due to the knowledge of their understanding of how the stains work and how the products work to remove them. The name given to making of these soaps is called saponification and involves the hydrolysis of fat. Now we've just made esters, and fats are esters, and in this case they're made from glycerol and our long-chain fatty acids, which are a carboxylic acid. So you can see glycerol there ending in the OL. It's a type of alcohol, and we know from using and making our esters yesterday that an alcohol plus a carboxylic acid makes that ester. And if we have a look here, we can see here is our fatty acid that is used. It's a long chain fatty acid. So you can see here we've got a CH3, CH2, there's 15 of those, another CH2 before we add our carboxylic acid chain. So we're looking there at 15, 16, 17, 18, 19, 20 carbons on that chain. Then we've got our glycerol. It's in a different form to what you've seen before, where we've mainly looked at our single ones with only the one on there, the one hydroxyl group, but here we've got a 3-hydroxyl group there. Its name given is our glycerol. So if we look here, when we combine those two together, you can see again, here's our 3 chains from our glycerol, and then our fatty acid is linked with that oxygen all the way across there. So that's our general soap. So how do we make this? It is then used by heating that fat that we've made with some concentrated sodium hydroxide. And when that sodium hydroxide reacts with the ester that we have, the fat that we've got, we get a salt. And soap is actually that product of the that reaction, and it's the salt of that fatty acid. And you can see in this chain here, we've got a very long chain, and down this end, we've got our oxygens, those 2 oxygens there, and here is the Na making it that salt. So how do they actually work? Soaps are amazing at how they do their job, and so when we look at a soap chain, I suppose, we've got a hydrophilic end and a hydrophobic end. So the word hydrophilic is water loving, and hydrophobic, as with any phobia, it's a fear or a dislike of, and in this case it's a dislike of water. So we have the head and the tail. The head is water loving and the tail is water hating. So what's actually happening in these chains is when we've got a small amount of soap dissolving in the water, so our soap, it's in the water, it's lathering up, the anions, the negative end, is accumulating at the surface with their tails up, and the heads are buried into that water there, and that surface tension is reduced as this happens. Now you can see in our diagram here along the top we have all our heads onto the water, our tails popping up in the air. Now down here we have got what we call a micelle, and we'll talk about that next as we're looking at how it actually removes the dirt and the grime, reducing water tension is one part, and then looking at how it actually goes about removing the grease or whatever. So here, when we dissolve those soaps or detergents into the water, it lowers the surface tension. So what actually happens is the surfactant, so the soap, that's another name for a soap or a detergent, it breaks the hydrogen bonding between the molecules, and the water spreads out then across the surface. So we actually call that like a wetting agent. There are sometimes we pop some water on our clothes and it just beads there. It doesn't actually soak in, it just beads along the top. Well, a surfactant helps to break that down and acts as a wetting agent and allows that hydrogen bonding to pull apart and actually allow the surface then to get wet. So you can see over here we normally get our water droplets forming, and they are pulling each other close together. It's a really strong force pulling them together, giving that beading sort of surface. Now, when we actually have higher concentrations, what happens is the soap molecules then cluster together, and here again we've got our hydrophobic tails are now attracted inwards, and our hydrophilic heads are facing outwards and surrounded by the water molecules, and we call that a micelle. So what happens is our soaps and detergents are surfactants, so the wetting agents breaking down that surface tension, but they are also an emulsifier. And if you think of an emulsion being like when we add vinegar and oil together for a dressing, they tend to separate there. If we add an emulsifying agent, often we can use that and it breaks that down, allowing them sometimes to mix a little bit more. So our soaps and detergents not only are a wetting agent that break down that surface tension, but they're also an emulsifier. They allow those different substances to mix. And as you know, oil and water don't mix, and so then just normal water won't clean the oil stain on your clothes. So what happens when a soap does come in contact with the grease? The non-polar tails of the soap, so that's that hydrophobic end of the soap molecule, is actually able to penetrate the oil stain. So it penetrates that oil stain. The polar head is attracted then to the water. So we've got the negative part embedding into the stain. The polar part is attracted to the water, and it actually pulls apart that the soap particle is pulled towards the water by that attractive force, and the oil comes with it with its hydrophobic end. With a bit of agitation, that'll actually help to lift that soil or that oil particle from the fabric then. Now what happens is then it's kind of trapped within that oil, within that micelle, and so then when we drain away our water, that happens as well. It goes down the drain. So if you think of dirty dishes, sometimes if you just wash your dirty dishes with a bit of water, it just droplets all over. It doesn't actually break it down. By adding some soap, it's reducing that water tension, allowing the soap to penetrate, and the two substances to mix. The hydrophobic end of the soap is attracted to the oil, the polar end is attracted to the water. It lifts that grease from the dishes and then goes down the sink once you're done. What's the difference then between a soap and a detergent? Well, a soap is a non-petrochemical detergent, whereas our detergents are actually made from our petrochemical products. So the petrochemical industry has actually developed a whole heap of detergents as an alternative to soap. Now, why would we do that? The one problem with soap is that in some hard water, so high levels of calcium and so on, they actually don't lather particularly well, and then it doesn't do the job quite as well. So if we've got high levels of calcium in our water, and sometimes you'll see that in terms of scaling on our shower heads and so forth, they won't lather as well. So a detergent actually is still able to lather in that hard water. And so they're also used more frequently because they actually don't produce scum. We'll discuss this a little bit more in class tomorrow and have a go at some questions as well and see how we can apply this knowledge in everyday life, but also to answering some of those famous HSC questions. See you then.